Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. I hope everybody's doing well. Today we are talking about a very important topic. We are talking about speed and velocity, and it's quite interesting because it relates to what we did last week with motion, right? So it relates to that. And so let's go. Let's see what we are talking about today. Motion, if you remember from last week, motion is the change of position relative to a reference point. Now, this is actually a very short lesson, and I've already done the answers on it, so I'm just going to be talking and explaining some of these answers as I go along. Let's have a look. So basically, here is a scenario. Once my sister talked to me into going into the roller skating rink with her. I hate skating, but against my better judgment, I agreed to go. I can skate, but I don't go very fast. At the rink, there were these speed skaters, or as I like to call them, assassin skaters. Okay, the assassin skaters weren't ridiculously fast. They were probably going approximately 20 miles per hour in the same direction as me. They zipped past me, just barely missing me. The worst part about going skating was getting stuck behind a group of skaters or a couple. They went so slowly that you had to speed up to get around them. Okay, so we've all been there. We've all been to the ice skating rink. And yes, we've all seen examples of people that are just really, really good at skating. And they're probably the same people that just go on a weekly basis or whatever. Um, Obviously, people are traveling at different speeds. So the first question asks, do all skaters in the rink move at the same speed? And the answer to that is obviously no. It's no. They're not traveling at the same speed, obviously. And that is relative to each other. So some people are slow, some people are fast, relative to each other, but also relative to the rink itself. Next question said, describe a sport or activity in which speed is important. Well, I would actually turn this around and say, I dare you to describe a sport or an activity where speed is not important. Because even golf, you have to think about the speed of the ball. Boxing, you obviously have to punch really quickly and you have to dodge really quickly. So I would say it's very hard to think of a sport where speed is not important. I chose football, racing, and swimming, but certainly almost every sport out there, speed is very, very important. Um, yeah, so let's go to the next one now. Here we have here we have the formula. The famous formula. So let me just read through this. You might describe the motion of an airplane as fast or the motion of a snail as slow. But using these words, you are describing the object speed. The object speed. So the speed of an object is the distance the object moves per unit of time. So if I cover a certain distance in a certain amount of time, that's my speed. And of course, some people say feet per second or yards per day. And it's all the same, it's all speed. If I say kilometers per hour or meters per day or meters per second, that's all speed. But the international standard unit is meters per second. Okay, meters per second. Now that's not to say that you couldn't use anything else, but that is the standard international unit. And why do we have standard units? So makes it easier for scientists and for people to understand each other. So if I'm talking to somebody in France or if I'm talking to somebody in Japan and I say 12 meters per minute or 12 meters per second, they understand what I'm talking about. Okay? The formula for speed is distance divided by time. And over here we have a triangle that shows this relationship. So speed equals distance over time. Now, I hope you're familiar with triangles. If you want any part of that equation, what do you have to do? You have to cover it up. So if I'm looking for distance, then it's going to be speed times time, isn't it? If I'm looking for speed, it's going to be distance divided by time. And if I'm looking for time, it's going to be distance divided by speed. And here we have an example, and it says, sorry, I'm just over here at the moment. Bear with me. It says, for example, at its cruising altitude, an airplane might be traveling at a constant speed of 260 meters per second. This means that the airplane will be traveling a distance of 260 meters every single second. Yeah, very crazy, but it's true. And the snail might be moving at 1 millimeter per second. So it depends on the object, obviously. Right, let's look at the next part here. We've got a cyclist, and they are traveling at a speed, a constant speed of 10 meters per second. Now, that's very interesting. The word constant. The word constant means not changing. Not changing. That's what constant means. So we've got the cyclist who's traveling at a constant speed of 10 meters per second, and we've got a question to answer. So how far would they have traveled in 1 second? In 1 second, they would travel 10 meters. What about after 2 seconds? Where are they going to be? They're going to be at 20 meters. Why is that? Because every second they're traveling 10 meters. So if 2 seconds have gone by, then they've traveled 20 meters. 3 seconds, 30 meters, and so on. And at 3.5 seconds, they would have traveled 35 meters. And at 4 seconds, they would have traveled 40 meters. Now, the next part is a question. It's a bit of a challenge. How long will it take the cyclist to travel 400 meters? Well, how long? How long? How long? So they're looking for time. We are looking for time. So what do? How do we work out time? Time is going to equal distance over, distance over speed. That's how you work out time. So we've got 400 meters divided by 10 meters per second, which is going to be 40 seconds. Okay, and that's how you work that one out. Okay, over here we've got average speed. Now we've got a scenario. So there is this competition. We call it Ironman competition in New Zealand and Australia. And it's a very, very tough competition. You have to be a top athlete to take part. And basically, it's a race where you take part in 3 different legs, so 3 different parts. You've got the swimming part, you've got the cycling part, and then you've got the running part. That's what you have. You have 3 different parts in this race. And your total average velocity is going to be the total distance divided by the time. Okay, the total distance divided by the time. So here we have an example. We've got somebody who has gone for a swim 3 kilometers in 1 hour, and then after swimming, they've cycled 50 kilometers in 3 hours, and then after cycling, they've done running 12 kilometers in 1 hour. Now the question is, what is their average speed? Nothing changes, boys. Nothing changes. It's still going to be speed equals distance divided by time. We have the total distance. Yes, we do. 3 kilometers plus 50 kilometers plus 12 kilometers. 3 kilometers plus 50, that's 53, plus 12, that is 65 kilometers. That's the total distance. What's the total time? They've covered swimming in 1 hour, cycling in 3 hours, and running in 1 hour. So that's going to be 5 hours. 65 divided by 5, they are traveling at 13 kilometers per hour. Okay, and that's how you work out the average time. It's just basically distance over the average speed. It's distance over time. Okay, so now we have a question to answer. We've got 2 athletes, 2 triathletes who took part in this race. And so triathlete A and triathlete B, let's just call them Ali and Bilal. And we're trying to work out their average speed. So the average speed for the swimming part is going to be distance over time. And that's going to be 3 kilometers divided by 0.8 hours, which is what I have here. And that's going to give me 3.75 kilometers per hour for Ali during the swimming. For Bilal during the swimming, it was 3 kilometers in 1 hour, which is 3 kilometers per hour. So clearly, in the swimming part of the race, Ali is traveling faster than Bilal. Let's look at the next part, which is biking. Now this time they had to cover 50 kilometers in a certain time. Well, Ali covered the 50 kilometers in 3 hours, while Bilal covered the 50 kilometers in 2.5 hours. Okay, so definitely different times there. Now, common sense tells me that if somebody covers it in less time, that means they're going faster. But once I did the calculation, so I've got speed equals distance over time, 50 kilometers in 3 hours for Ali. That means Ali was traveling at 16.7 kilometers per hour, which is very fast. But then look at Bilal. Bilal was traveling even faster. He covered the 50 kilometers in 2.5 hours. So Bilal was traveling at 20 kilometers per hour. So who's faster? Bilal. Bilal actually made it up. So Bilal was faster at biking, even though Ali was faster at swimming. But Bilal made up for it in the biking, didn't he? Very good. Moving on. Instantaneous speed. Now here we're talking about something else. Instantaneous speed is your speed at a certain time, at a certain moment in time. What does that mean? Let's say, for example, I'm traveling from city A, let's call it Salmiya, to city B, which let's call it Mangaf. Okay. And so obviously along the way, I'm going to stop, I'm going to speed up, I'm going to slow down, I'm going to accelerate, I'm going to decelerate, I'm going to change directions. That's what happens when you're driving. You might stop at a traffic light, you might slow down as you're going around the roundabout, and so on and so forth. So my instantaneous speed, as this definition tells us, I'd like you to highlight this in your book, is the speed at which an object is moving at a given instant in time. So it's important not to confuse instantaneous speed with average speed. Average speed is your speed across the journey, the kind of the mean, the what's your general speed for the whole journey. It's that. Whereas instantaneous speed is your speed at that instant. So over here, for example, as I was passing Salwa, my speed was 100 kilometers per hour. Whereas over here, as I was passing Mahbula, I might have been 0 kilometers per hour for that one time when I was at the traffic light. And over here, as I was doing a turn somewhere, maybe perhaps near Agela, I was going at 56 kilometers per hour. So my instantaneous speed is the speed at that moment, okay? And over here, we've got a question to do. So let's see if we can do it. It's asking, use the data from all three legs to solve for each triathlete's average speed. So what do we have here? We have the third part, the running, and we've got 12 kilometers. Now, Ali has covered the 12 kilometers in 1.2 hours, while Bilal covered the 12 kilometers in 1 hour. And so using that, I can work out the speed for Ali in that last part, which is 12 divided by 1.2. 12 kilometers, that's the distance, divided by the time, 1.2 hours, and that equals 10 kilometers per hour. So that was the speed of Ali towards the end. The speed of Bilal towards the end was 12 kilometers per hour. How do I know that? They've covered 12 kilometers in 1 hour, so that's just 12 kilometers per hour. And then it's asked me, identify which athlete finished first. So I need data from all three. So over here, Ali was traveling, let's see, 3 kilometers plus 50, so 65, and average speed. We're looking for average speed. Oh, not just here. So this is not correct, is it? This is just for the last part. Let's do it. Let's do it together. So the total distance for the race is actually 65 kilometers because it's part A, part B, and part C. Triathlete A's total time. So Ali covered it in 0.8, 3, and 1.2. So Ali covered it in 5 hours. 5 hours. That's why it's important to read the question. Triathlete A's average speed is going to be 65 divided by 5. 65, which is total distance divided by 5 hours, and that's going to be 13 kilometers per hour. That's what that is. What about B? Triathlete B's total time, so that's going to be 1 hour here for the running, 1 hour. Sorry, for the swimming it's 1 hour. For the biking it's 2.5, so that's already 3.5, and 1 hour for the running, so that's 4.5 hours. 4.5 hours. And so what's going to be, it's going to be total distance, which is 65 kilometers, but they've covered it in 4.5 hours, and that's going to be faster than Ali, I think. 65 divided by 4.5, and that's going to be 14.4. 14.4. So clearly 14.4 is bigger than 13, so it's going to be B. Bilal won this over Ali. Okay, let's keep moving. How do you describe velocity? Now, simply put, velocity is speed, but now it has a direction. So now speed and a direction equals velocity. I'm going to read through this and then we're going to talk about it a bit more. Knowing the speed at which something travels does not tell you everything about its motion. To describe an object's motion, you also need to know its direction. For example, suppose you hear that a thunderstorm is traveling at a speed of 25 kilometers per hour. Now that's fast, but I need more information. Why is that? I want to know if that thunderstorm is coming towards me, if it's going away from me. If it's coming towards me, then I should be worried. If it's going away from me, then I'm not so worried. So here's an example of a situation where direction is very important. Um, so let's have a look. So when you know both speed and direction of an object's motion, you know the velocity of the object. Did you hear that? So the velocity of the object depends on both speed and direction, which is why I've got this over here. Okay, so that's very important. Speed in a given direction is called velocity. You know the velocity of a storm when you know that it's moving at 25 kilometers per hour, so that's speed, eastward, so that's direction. So it's moving eastward, and now I know the direction. At times, describing velocity of a moving object can be very important. For example, air traffic controllers must keep close track of the velocities of the aircraft under their control. These velocities change as airplanes move overhead and on the runway. An error in determining a velocity, either in speed or in direction, could lead to a collision. Velocity is also important to airplane pilots. For example, the stunt pilots in Figure 2 make spectacular use of their control over the velocity of their aircraft. Absolutely. Now, so we've seen this during National Day celebrations in Kuwait. So we've got these Blue Angels, they're called, or whatever, those stunt pilots, and they have to be very, very careful with their speeds, but more importantly, they also have to be careful with their direction because they don't want to hit each other. They want to be going perfectly at the same angle. And if one of them is traveling sort of west and the other one's traveling east, then they're not going to look as impressive. But what they do is they travel together. So they're very aware of their velocities, speed and direction, velocities, which is a vector quantity for those of you that are interested. Right. So here is a scenario with somebody whose name is Mario. Mario is planning on riding his bike from his home to the baseball park. So here's his home and here's the baseball park. Okay? And what's going on here is that Mario is going to travel west and then he's going to travel south and then he's going to travel west again. Now the map shows the route that he will be following, and on the map 1 centimeter is equal to 100 meters. 1 centimeter is equal to 100 meters. So that's called a key, a scale, okay? Um, right. Use the metric ruler to determine how far west and how far south Mario has traveled. Now I measured this on my PowerPoint slide presentation, and it's not the clearest, so I want you to try and do it in your own books. But basically what we have here is 6 centimeters to the west, 5 centimeters south, and 3 centimeters to the west again. So it's asking you how far west they've traveled. They've traveled 6 and 3, so that's going to be equal, totaling 9 centimeters. Now remember they told us each centimeter is 100 meters, so that's going to be 900 meters west. That's what the W is for, 900 meters west. And how far south have they traveled? Well, that's easy as well. We've got it right here. Oh, sorry, just a second. Let me just move my face out of the way. Oh, that's not how you move. Well, I suppose that works. Okay, that works. That's better. Very good. So how far south have they traveled? Once again, that's going to be, oh, let me just put this ever so slightly up. Nope, 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 nope. There we are. They've traveled 5 centimeters south, so that's 5 centimeters south is equivalent to 500 meters. And once again, we have to remember the direction because it's asking for velocity. And then it's asking us to calculate. Now, this is a very interesting question. Calculate the speed, the average speed for Mario, who has to meet their friend at noon. Noon is 12 p.m. and they are leaving the house at 11:55 a.m. So that means they're going to get there within 5 minutes. How much do they have to travel? The total distance they have to travel is 900 meters west plus 500 meters south. So that's 1,400 meters. That's the total distance. The time is 5 minutes. What's 5 minutes in seconds? 5 minutes in seconds is 5 times 60. If you know your times tables, 5 times 6 is 30, 300 seconds. So that's the total time. So we've got distance, we've got the time. Can we work out the speed? Of course we can. Speed, if I cover speed up over here, if I cover speed, then it's going to be speed is equal to distance over time, which is 1,400 meters divided by 300 seconds, which is 4.66 meters per second. Interesting. That's how you work that one out. Let's go to the next question. Assess your understanding. How do you describe motion of an object? First, you have to know about the change in position relative to a reference point. And the second is the speed and the direction, which is the velocity. Where has the object traveled to, or how fast it has traveled in a unit that we all understand, and which direction. So that is a complete description of the object's motion. Okay? And now I know that the velocity of an object is the speed and direction. Okay? And it's going to be distance traveled in a certain time with a direction. Okay, how do you graph motion? Very, very easy stuff. Hopefully most of you remember this from maths, but if you don't, I will explain it. So just remember this formula here. That's what today's lesson is about. Speed equals distance over time. Now it turns out you can actually graph this. If you look at this formula, what we do is we actually, when we're graphing motion, is we put distance on the y-axis and we put time on the x-axis. Okay? Distance on the y, time on the x. Now it turns out speed is distance divided by time. So we've got distance here, we've got time here. So what do you think this slope represents? This slope here represents speed, right? Interesting. So the slope, or how steep the graph is, represents speed. So if we have a graph that's this steep, then that's fast. That's slower, that's really slow, and that's slowest. Okay? So how steep the graph is represents how fast the object is, generally speaking. Let's have a look over here. So slope is equal to rise over run. Rise is in the y-axis, which is the distance. Run is in the x-axis, which is the time. And so if over here, for example, I'm trying to work out the rise over the run, I have the rise, which is 1,200 minus 800, which is 400. And then I have, excuse me, and then I have the run, which is 2 minutes. So since slope is rise over run, it's going to be 400 divided by 2 minutes, which is 200 meters per minute. Okay, and if you're not sure about that, just pause the video, think about it, do it again, and watch the calculations. If you're still not sure, please come and see me. Different slopes. So here we have an exercise to do. How do we calculate the rise over the run, or the slope in each part of this graph? So we've got three parts. We've got part A, we've got part B, and we've got part C. In part A, the rise is 600. How did we determine that? Well, there it is. It goes from 0 at the bottom, that's, remember, the y-axis, 0 to 600. So it's going to be 600 for the rise. What about the run? The run is the x part. So it goes from 0 to 4. So that's going to be 4. So it's going to be 600 divided by 4. 600 divided by 4, if you were to do that in your calculator, you can do it in your head, it's going to be 150 meters per minute. 150 meters per minute. So that is the rise, that is the speed, or the slope over here, 150 meters per minute. Right, let's look at part B. Part B, what is the rise in part B? Well, we started at 4, at 600, and then we ended up at 600. So we haven't really moved. So the rise is 0. What about the run? We started at 4 minutes and we ended up at 7 minutes. So there's about 3 minutes there. And what's the slope? The slope is going to be 0 over 3. 0 over anything is 0. So that's going to be 0. And that makes sense. 0 meters per minute. We're not moving. For 3 minutes, we're not moving. What about the last part? Well, we've got 600 here. at 7 minutes, and at 10 minutes we've got, what have we got? 1,200. So the total rise is going to be 1,200 minus 600, which is 600, divided by 3 minutes, which is 200 meters per minute. So this is going to be 200 meters per minute. So very good. So now it's very clear. We can see that the person was going at 150 meters per minute, which is fast, but then they stopped for 3 minutes. Maybe they were taking a break, drinking water, or whatever, or using the bathroom, and then they went really fast the last 3 minutes. So they were maybe saving their energy towards the beginning, then they stopped for a little while, and then they were going really fast at 200 meters per minute towards the end. And we can see that this is steeper, and the reason why it's steeper is because they were going faster. Okay, let's have a look here. So identify what is the thing, the what of a distance time graph shows you the speed of a moving object. So slope is the speed. The slope, the gradient is the speed. Part B, calculate the rise of a line on a distance versus time graph is 900 meters and the run is 3 minutes. What is the slope? Remember, slope is rise over run. We've got the rise, which is 900 meters. The run is 3 meters or 3 minutes. 900 meters, 3 minutes. 900 meters in 3 minutes, 300 meters per minute. There's the calculation for you. 300 meters per minute. The last part is it possible for a distance versus time graph to be a vertical line? So this is what they're asking us. Is it possible for it to be a vertical line? An instantaneous vertical line? Not really. I can't think of an object that's going to go from 0 to 100 and then back to 0 instantaneously. Maybe light is the closest thing, but for 99.999% of scenarios, that's not going to happen. It's possible for an object to be. It's possible for a distance time graph to be a horizontal line. It just means the object is not moving. It's stuck at a, it's just stuck at a traffic light or something. But this scenario here represents an object that is moved instantly, like from 0 to a million in a microsecond. So it's not really possible. Anyway, boys and girls, and with that, we have finished the lesson. I realized I was going through that a bit quickly, but I wanted to keep it short and sweet. Please go back and revise some of those aspects if you're not sure. And if you have any questions, don't hesitate to ask me. Thank you very much. Over and out. I'll see you in the next one.